Okay, Chapter 6, Discrete Probability Distributions. So the concepts that we're going to cover in this chapter and that you'll be quizzed and tested on are basically the concept of what we call discrete probability distributions. On a couple of the slides, I'm going to talk about some definitions in terms of what we call a random variable, and then I'm going to talk about some rules about how to set up a discrete probability distribution. We'll talk about an expected value variance calculation, and then the two unique types of discrete distributions we're going to look at in this particular chapter is the binomial distribution and the Poisson distribution. Note, I am not going to be covering the hypergeometric distribution. That's the one that we're not going to do. So once we get to the Poisson, that'll be the end of chapter 6. Okay, and a couple basic definitions. So when you start to read about what's called a random variable, that's basically just a numerical description of an experimental outcome. So like, for example, if you tossed a coin one time, you can say that there's two outcomes. There's going to be a heads or a tails, and we're going to describe those outcomes basically as what we call a random variable. And then, of course, in this chapter, we're going to go over what's called the discrete random variable, which basically the random variable, which we're going to define as x, can said to assume any number of either finite number of values or an infinite sequence of values. And we're going to go over a couple examples in a couple slides in a moment just to demonstrate those. The other type of random variable is called the continuous random variable, and that's what we're going to cover mainly in chapter 7, going back to the normal curve type of calculations. But that's more of where when you're looking at random variables, you're looking at intervals or ranges of values because of the continuous type of concepts such as like age or time. So again, this chapter is all about the discrete random variable. So a discrete probability distribution, in a moment you're going to see, it's basically where, I'm going to write this right down here at the bottom of the slide, where we're going to set up, for example, one column, we're going to label it as x, and then the next column we're going to label it as f of x, which means probability. And basically in the x column, we're basically just going to list all of the outcomes that the random variable could represent. And then in this column, we're going to basically be assigning probabilities to each one of these outcomes. And the probabilities that are assigned to each outcome and the way that they're distributed is going to be called basically your probability distribution. And you'll notice that eventually this should look a lot like, I'm going to write this right over here, a lot like a relative frequency distribution. In fact, it's exactly what it is. In fact, that's what we did back in chapter 2. And a couple basic rules, just to remember that whenever you are assigning probabilities, that the range of probability assignments go from 0 to 1. That's basically what this first box is saying. And then the second one, the second basic rule is that the sum of all your probabilities have to equal 1. That's what they're trying to tell you. Those are two basic rules of probability. So in this discrete example, we're going to let x represent the number of TVs that were sold at a store at any given day. And so in the example, you're going to find out that they did the study, I believe it was over like 200 days, and they figured out that x basically could take on values of 0, 1, 2, 3, or 4 TVs that were sold on any given day. So again, this is based on just, observing exactly what's going on each day in the store, and they found that at any one day, these were the values that x could represent. And then in a moment, I'm going to show you how the distribution looked like. Okay, for this discrete distribution, notice in one column we've got the units sold, so that would represent the number of TVs that are sold on any given day. And in this column, this represents how many days they made their observations. And at the bottom, you notice you see 200. So what they did was over 200 days, this is what they observed. And so, for example, on 80 of the days, they sold 0 TVs. On 50 of the days, they sold 1 TV. On 40 of the days, they sold exactly 2 TVs. And then on 10 of the days, they sold 3 TVs. 20 of the days, they sold 4 TVs. So then what they did was they took these numbers and they converted them into a relative frequency or probability by simply taking 80 divided by 200, so they got 0.40. They took 50 divided by 200 and they got 0.25. They took 40 divided by 200 and they got 0.2. They took 10 divided by 200 and they got 0.05, and then they took 20 divided by 200 and they got 0.10. So basically they took each of these numbers and divided by 200 and what they came up with was these probability distributions. And so I'm going to write probability over this column. And you got the f of x function, which that also means probability. You may see in your textbook they may also describe this as p parenthesis x. But notice, if we add up all of these probabilities, you do get 1, and that follows your basic rule of probability. So this is how a discrete probability distribution would look like. And also notice it is discrete because x can only assume a finite number. X in this case can only be 0, 1, 2, 3, or 4. And this is kind of review from the previous chapter in chapter 5, but basically you could have a discrete probability distribution where the outcomes are equally likely, and if you get that, it's the same type of formula we used back in chapter 5. It's basically 1 divided by n, where n represents the number of outcomes. So that part really is review. Now, a couple new formulas on this concept of what they call an expected value or variance of a discrete distribution. So the first one I'm going to walk you through is here's this symbol mu, and the formula is going to be to multiply x times its probability and then add it together, and we're going to call that the expected value. And then the next calculation I'm going to show you is how to do the variance for a discrete distribution, and we're going to go over this formula right there in a couple of slides. And then finally, the standard deviation is always going to be the square root of your variance. So back to the TV example, to calculate an expected value, you simply take x, which is right here, and the probability of x, which is right there, and what you're going to do is you're just going to multiply them. And then you're going to get this column, which we're going to describe as x times f of x. So you take 0 times 0.4, you get 0. 1 times 0.25, you get 0.25. 2 times 0.2 gets 0.4. 3 times 0.05 gets 0.15. And then 4 times 0.1 equals 0.4. So once you do that, you add this column together, and you get 1.2, guys. That's going to be our mu value, or our expected value. Okay, and so for this particular case, on any given day, you would expect to sell about 1.2 TV. So it's kind of like a weighted average type of calculation. So again, x times f of x, you set up this column, you add up the column, you get this value. It's called the mu value, 1.2. They call that the expected value. Now, once you get this is the value you're going to use in the next calculation when you do the variance. Okay, so just to remind you, the mu value, or the expected value we're going to be using, is mu is equal to 1.20. That's TVs per day. And notice we've got our x column right here. We've got the x minus mu column. We're going to have x minus mu squared. Here's our probabilities that we already calculated. And then here's where you take your squared column and you multiply by those probabilities again. So in the first column, you simply take 0 minus 1.2 gets you negative 1.2. 1 minus 1.2 gives you negative 0.2. 2 minus 1.2 gives you 0.8. 3 minus 1.2 gives you 1.8. And then 4 minus 1.2 gives you 2.8. So then after you get that, you go to the next column and you square everything in this column. So negative 1.2 squared gets you to 1.44. Negative 0.2 squared is 0.04. 0.8 squared is 0.64. 1.8 squared is 3.24. And then 2.8 squared is 7.84. Now, once you've got your squared column, you take each of these numbers and you multiply by those same probabilities again. So it'd be 1.44 multiplied by 0.40 gives you 0.576 and so forth. So I'm just going to make a note that you multiply these. And then once you get everything multiplied again by the squared numbers, you simply add them up. And this number here with the sigma squared is called your variance. And then to get the standard deviation, you simply take the square root of 1.66, and that's going to give you about 1.28. And that's how you would get your standard deviation. Okay, so a binomial distribution has 4 distinct types of properties. And note, this is going to be 1 or 2 discrete probability distributions we're going to be doing. And the basic idea is that you have an experiment that consists of identical trials. We're going to only look at 2 outcomes, and we're going to label those outcomes as either success or failure. And then we're going to have a constant probability. It's called the probability of success, denoted by the letter P. Now, in your textbook, they like to use the pi symbol for this, and I think that can be confusing. So I'm going to show you a couple formulas in a moment, and rather than using the pi symbol, I'm going to simply use the letter P to represent the probability of success, and that's said to be held constant for each trial. And then the other rule is that the trials are said to be independent. Now, when we look at any binomial problem, and we're going to be using probability tables to do your calculations, we are always going to be interested in what we call, our interest is the number of successes, not the number of failures. So X is going to represent what we label as the success, and we're trying to figure out what's our number of successes given how many trials are in the problem. So typically what you'll see is you'll have N, which is representative of number of trials. You're going to have a P, which is going to represent the probability of success. And then once you know these numbers, typically then we're going to go to our table of probabilities, of binomial probabilities in your appendix to actually get the actual probabilities for each outcome. This is your basic probability function. I am not going to require you to do any of these manually, but note you have one part of this probability calculation where this is your combination formula. P obviously represents your probability of success. You've got 1 minus P, which represents failure, and then notice you've got your X, which represents whatever outcome you're looking for. But the point is, if you would to put this calculation for whatever you want X to be, this would give you the probability. Now, because of the factorials and all the crazy calculations, again, I'm not going to make you do this. We're going to be using the tables. The tables will give us all of the answers that you're going to need. Now, here we're going to notice that this is going to differ just slightly just in terms of labels, but I like this formula better. We're going to use this NP as how to calculate the expected value of a binomial. So in your textbook, they like to use N times pi. I like to use N times P. I'm going to use P instead of the pi symbol. And then same thing with your variance. I'm going to say it's NP times 1 minus P. In your textbook, it's going to use that pi, N times pi times 1 minus pi. I think that can be confusing because you might think that that's supposed to be 3.14. So rather than doing that, I'm just going to say use NP times 1 minus P to get your variance, and then you simply take the square root of that to get your standard deviation. So the only thing I'm going to differ, just to try to help simplify this chapter a little bit for you, is rather than the pi symbol that they use, I'm going to use the letter P to represent the probability. And then basically after that, we're simply just going to be in the appendix using the tables. Now, the final distribution we're going to look at is what's called a Poisson distribution. And the Poisson distribution is where we're going to estimate occurrences giving a certain time interval or space. X is an infinite sequence. You don't put a cap on it, but it's still discrete because X can assume an infinite sequence of values. And so in a moment, I'm going to walk you through what the formula looks like, and we also have tables in the back of the book that we're going to use to calculate the probability. So a couple properties of the Poisson is, number one, is that the probability of an occurrence is the same for any 2 intervals of equal length. So if you're looking at time, whether you're saying from 6 to 6:30 or 6:30 to 7, if it's still 30 minutes, the probability of an occurrence is going to be the same regardless of what part of time you're looking at. So as long as it's the same equal length of time, that's one of the properties. And then I'll just kind of focus on the occurrence or non-occurrence of the intervals, or that independence concept as well. And that's just a couple properties of the Poisson. Now, if you look at this formula, note that it's mu to the x times e to the negative mu divided by x factorial. Again, we're going to use the tables in the back of the book. You're welcome to plug this into your calculators. This one is doable, I think, but where you got mu is the mean. The mu value is the one we're going to have to look for because that could change. That is, again, I'll remind you, that is your expected value. given a specific time interval. Here's your natural logarithm, so that's kind of defined within the problem. So your key eventually is going to figure out what is that mu value before you can actually look it up in your probability table.